All right, thank you very much. Yeah, thanks for having me. So do this presentation the second time around now, so see how I go. I'll try not to repeat myself too much.
No one hears it, so you're good.
Excellent. So, yeah, I've been working in this space for 15 years or so now. It's getting very noisy as I'll sort of go through. I mean, I think the sugarcane industry has probably not had the same exposure as some of the other industries I work with. A lot of our work at the moment is in the beef grazing industry, doing a lot of work with Meat and Livestock Australia and their Carbon Neutral 2030 program. And I suppose in the midst of this sort of research that we're doing, we also have this what's happening with the federal government and their allocation of carbon credits and there's all that other stuff going on. So, you know, as a scientist, we're after science. We want to try and make sure that, you know, all this stuff is rigorous and I suppose try and promote best practice. I mean, just to avoid, particularly for farmers and I suppose the people that I see at risk of being ripped off in this space because there's a bit of a new industry and it's a bit of the Wild West at the moment. So I suppose a bit of a cautionary tale. But also, specific to the sugarcane industry, I'll run through a few things and I suppose see what is on the horizon there as well. So basically just cover very briefly, you know, what are we talking about when we talk about this natural capital or carbon stuff? What are the opportunities to increase carbon sinks? Soil carbon, obviously, that's one of the most potential and also the most sort of noise within the media. I'll explain a little bit about what we're doing to try and hopefully, you know, reduce some of that noise, to reduce those uncertainties, and then I'll go on to the nitrogen side of things. So we basically have carbon being sucked into our system through photosynthesis. That's what forms the basis of these carbon offsets or carbon sinks. But then we also need to consider the source side of things. So where are our greenhouse gases coming from within our agricultural systems? And nitrogen management is actually the key one there. So we'll have a look at that. You know, right rate, you know, 6 easy steps, all that gizmo. I won't go into too much detail, but I'll focus on probably a small part of that. And then also cover some of these emerging technologies, which I see will probably have a greater role to play in the future of the sugarcane industry. So very briefly, difference between a carbon offset and a carbon inset. So offsets are generated by the farmer. You know, your soil carbon is an offset. If you're growing sequestering carbon through vegetation growth or trees, that could be an offset. But what you choose to do with it, you could either offset it by selling it to somebody else, and that somebody else, it could be a third-party supplier, it could be someone like McDonald's, or it could be a coal mine, and we use that to reduce their emissions. So it's basically leaving your farm and going off to someone else's farm to reduce someone else's emissions. Now, because it's going somewhere else, I mean, you know, the coal mine's going to burn there, so the power station's going to burn the coal. It's going to happen anyway. There needs to be a much higher level of rigour associated with that. So it's, you know, actually the accounting for that is actually pretty high. As you'll see, it's probably not high enough, or there's some bugs in the system that we need to iron out, but it's a pretty emerging market. But you can't double count. You can't have your carbon offset and eat it as well. Carbon inset's about keeping it within the supply chain. So instead of you selling it to someone else, you basically use it, you know, to offset your own emissions from your own business. So if I'm a beef farmer, and I basically inset my emission, then I can sell that as carbon neutral beef. I can't sell it to somebody else as an offset and then also claim the carbon neutrality. So a bit of a difference there. But the advantage I see in the carbon insetting space is that, you know, because, you know, you're not so much relying on someone else, you know, emissions that you need to reduce. You're only reducing your own emissions. There's a bit more flexibility in the system as far as how we actually measure that stuff. The rigor's not so important. The rigor's not so strict, I should say. It's still very important, but not quite as strict. And there's all the other things you can do as well. So biodiversity offsets, biodiversity insetting, or soil health, or other things you can potentially include in there as well. So it's a bit more flexible and a bit more things we can start to look at. So when we start to talk about natural capital then, it's not just carbon, it's all these things. And, you know, reef credits are touching that already. There's lots of stuff in biodiversity space. For this presentation, I'm only really going to be talking about productivity, because, you know, you need to, you can't be green if you're in the red. Soil health and carbon stocks, because a lot of these things go, you know, hand in hand. And also nitrous oxide. So these nutrient greenhouse gases, so when we talk about nitrogen fertiliser, the key one we're chasing here is nitrous oxide. So this is a major source of emissions from farms. I'll talk briefly about how we go about, you know, what we're doing from a technology point of view to, you know, measure these things. And importantly, how do we measure them cost effectively? Like, how can we actually do these things at a cost which is not going to, you know, lead to a negative return? One of the challenges with, you know, all these, particularly the offsets, is they're very, very expensive. First of all, to baseline, to come back and resample, and then to audit. And there's, you know, a lot of costs associated with that. So reducing the costs of, you know, measuring that carbon or reductions in greenhouse gases or whatever it is really important. There's also very good work going on in the biodiversity space, but I won't really talk about that today, but, you know, things like acoustic sensors, so soundscapes, you know, tools that we can basically use to monitor biodiversity, on-land biodiversity, not reef stuff, on-farm biodiversity are progressing very far as well. So within the beef industry, I'm not quite sure how much of this has sort of come across into the sugarcane industry, but there's been some pretty, you know, significant announcements made. Now, an ACCU is the Australian Carbon Credit Unit. So this is basically the Australian government is buying carbon from the market, and the market's producing these ACCUs. So it's basically a commodity, but it's underpinned by the Australian government, which means, you know, this is a government-issued credit. So, you know, high rigour. And in the beef industry, we're now seeing these massive amounts of carbon being credited to these farmers, you know, for basically soil carbon. I'm not going to even talk about some of the revegetation stuff. You know, areas like Birdsville and whatnot are sort of changing the whole landscape around revegetation. I'm just going to focus on the soil carbon stuff. But even with that, there's still questions around, well, is that really valid? And that's where we come in as a science, because what the media is saying and what's happening from the government is not really what the science is saying, which is unfortunate. And it's significant. You know, in this case, this one farm, this is a single farm, received $3.3 million worth of carbon credits. So, wow. Yeah, it's massive. I mean, it's a 10,000 hectare beef grazing property. So, so you're talking, you know, potentially big bickies. And, you know, even if you break that down on a per hectare basis, you know, really quite valuable returns, you know, for land that's, you know, this is not intensive farming country, this is extensive grazing country. And so really talking about a bit of a game changer when it comes to the economics of it as well. And you might have seen beef be trying to become carbon neutral according to these credits and according to these proponents that are basically promoting these credits. Not only is the beef industry carbon neutral, but actually it's sequestering 50 times the amount of carbon that's being produced. So these are pretty unbelievable claims, and they're backed up by the Australian government, right? So trust me, I'm from the government. What these numbers come back to is just for reference to this number, 2 to 8 tonnes of carbon per hectare per year is what basically equals that. 2 to 8 tonnes. So unfortunately, that's not quite what the science is saying, and that's why this is so much of a messy space at the moment, is that you've got the industry promoting one thing, the carbon developers industry promoting one thing, backed up by the Australian government, and the farmers are in the middle, and the scientists are basically saying, well, wait a second, that's not quite right. So what does the science say? Well, beef grazing management, so if we look at things like herd rotation, time-controlled grazing, no change. So those 94,000 ACCUs were credited on grazing management. So this is a study I've just done, looking at time-controlled grazing. Okay, 0.3 to 0.5. That's a really good outcome. That's going to offset 30% of the potential emissions from some of these farms. That's a really, really good take-home message, but not 3 to 8 tonnes. It's very, very different. If you look at all these different things, cropping to pasture, tropical legumes, nowhere near the realm of basically what's being claimed through these carbon credits. And that's where the big challenge is like the science is saying one thing, and the carbon development industry, backed up by the Australian government, is saying another thing. So what's going on here? And just for reference, if we look at sort of sugarcane trash retention, we're basically looking at a 0.6 to negative 0.6, so it's actually emitted more, to 0.7 tonnes of carbon per hectare per year. Now, this is just the literature that's out there. This is just studies that have been published. There's, of course, other studies that, on things like cover crops and multi-species, which haven't come out yet, so this is not definitive, but basically just to give you an idea about the sort of ranges we're talking about. And really the issue being, what is happening in the media and what is happening in the science are very two different things. And why is that? Well, ultimately, there's an issue with the method. So the method is, signed off by the Australian government, but it's essentially flawed. Why is that? Well, there's a lot of variability in our soils. As anybody who you guys know who've done an EM38 map, you know how much variability is across your sugarcane paddocks. You look at a grazing property that might be 10 to 20,000 hectares, there's a fair bit of variability across that. It's very, very hard to measure that spatial variability. Not only that, we're measuring small amounts, 3.3 to 0.5 tonnes of carbon per hectare per year, in a background where we might have 100 tonnes of carbon in our soils already. That's historic carbon that's been there for 10,000 years. It's got nothing to do with the management change that you've implemented. So we're trying to measure basically the equivalent of throwing a spoonful of water into a bathtub. It's just really hard to detect that small change in the big background. But not only that, we also have this issue around climatic variability. I mean, obviously these are non-irrigated systems. We go through these ENSO, La Nina, El Nino cycles. This is my own cattle property down in Toowoomba. That's my daughter. Looking pretty good, 2014. Lots of carbon going in, sequestering lots of carbon. This is what the carbon stocks look like here, and across, we look at different soil types as well. But basically, there's this big driver, which is climate driving vegetation productivity, putting lots of carbon in. The challenge is when the taps turn off and it looks like this, we can actually lose most of that carbon, 30% in this case. So we have this massive climatic variability that's just related to the background cycles of El Nino, La Nina, whatever. And one of the challenges that we have with these carbon projects, they're 25 years and they get paid every 5 years. And these initial ones basically just happen to hit the jackpot. So they're basically baselined in 2016 and they were resampled about 2022 or so. So what happened in 2022? Well, it just happened to coincide with the third La Nina in a row. Quite unusual, but lots of vegetation growing, lots of carbon going back in. So not particularly carbon that's going to stay there for very long, potentially carbon that's going to come back out again. And we can see that here. We basically, we measured again, that's basically, I think it was 2019. We actually had that same uptick. Nothing to do with management change, just the climatic cycles. So that's one of the issues, is that there's basically been an over-crediting in this space because they've basically captured this climatic variability. Now, if we still get those 0.3 to 0.5 tonnes of carbon a year, that's really great. That's going a long way to offset our industry's emissions, but once again, it's not the 3 to 8 tonnes that we're talking about. We've got to keep this realistic. And the challenge is, it's very, very hard to measure, and it's very, very hard to actually sequester in the first place. So one of the things we're working with quite a lot now, when we come to the measurement side of things, is these what we call CO2 flux towers. What they do is they measure high resolution. We're talking every 30 minutes we get a reading of CO2, water, and energy. So CO2 goes into the plant soil system through photosynthesis. So we're basically measuring plants growing. We're measuring them every half hour, and we're measuring it over a pretty big area of, let's say 50 hectares. And so we get a nice big integrated number, and we get a really high resolution number. It allows us to basically account for all those peaks and troughs associated with the rain events and whatnot. It also gives us very good data for modelling. which allows us to really upscale. So we can basically feed this data into models and use those models to be able to put these carbon plans in place over large areas very, very cheaply. Now, we're working currently in the beef industry, in grazing pastures. We're moving now into cropping systems, but there's no reason this technology won't work everywhere. You know, it's a cropping system, and it's very robust. It also does water fluxes, and that's also a key one when we talk about water use efficiency. Water is our most limiting nutrient in our dry land systems, and so if we can optimise that water use a lot more, we can actually get really good carbon gains as well. So we basically run these out over most of Queensland, from up in the Gulf all the way down into New South Wales as well, focusing once again on grazing systems, a lot in the Brigalow belt around Rockhampton, in the Fitzroy catchment, out to Longreach. But looking at that whole, can we actually get a better handle on how we measure this stuff and how we can credit it? The technology itself is transferable across systems, and we're pretty confident with what we'll get is a pretty robust tool that can capture carbon and most importantly predict going forward through our climatic troughs. So we know we're not relying on just drawing 2 points of the line depending on the seasons. We can actually predict that moving forward. And most importantly, this is not technology that we came up with at QUT. This is technology that exists for about 30 years or so. A lot of it comes internationally as well. There's over $1 billion globally invested in these towers. So it's a very, very robust and very, very well-trodden technology. All these sites are the sites across Australia that are using these technologies within this sort of this network called the Terrestrial Ecosystem Research Network. Unfortunately, for the agricultural industry, apart from those two ones that are circled, which are the ones that are run by QUT, they're all in natural systems. So they're all on the Daintree rainforest, for instance, looking at carbon sequestration from the rainforest, or the tall eucalypts down in Tasmania. All the Kiwi ones are on dairy farms, so they're a bit more advanced. But unfortunately, this technology has not really been run out across agriculture. But we're trying to change that and trying to say this is a really good tool that agriculture industry can use to really reduce some of those uncertainties and try and get some really good, solid data behind some of the stuff. And ultimately, develop that into a platform. And the key thing here is, all this data we're collecting goes into calibrating models. Now, models, people use the term model, we use a model, we develop our own model. Rubbish in, rubbish out. So you need really good data going in, otherwise you get really good, really crap data going out. We just look at, maybe some of the stuff that BOM's doing at the moment. Their models, maybe, removing a lot of their weather stations is not such a good idea. But that allows us to really reduce the cost and really upscale that cost. And we're partnering, obviously, with MLA, but also this is through a partnership with a company called Agrimix, who are basically going to use this as a commercialisation tool. So hopefully we should have something to market in the next 12 months. So that covers the carbon stuff. I'll go now diving into the nitrogen. Now, being a room full of sugarcane farmers, I'm not going to go down this too much because I'm pretty sure you're sick of hearing about nitrogen. But there's a couple of things I want to talk about and how it relates to the climate side of things, and how, particularly when you start looking at carbon budgets and all that sort of stuff. Now, I mentioned nitrous oxide before that, little N2O. So nitrous oxide, it's only a very small part of the whole carbon cycle, but it's a very, very potent greenhouse gas. It's actually 300 times more potent as a greenhouse gas than CO2. So we all hear all this stuff about CO2, but actually, methane is a massive one for the beef industry, enteric methane production in the rumen, cow burps. But in cropping systems or sugarcane systems, the big one's actually nitrous oxide. And so, that's where most of our carbon footprint's coming from. This graph here is a bit hard to see, but basically the purple stuff here is from crop residues. So crop residues, when they break down, produce nitrous oxide. So that's a pretty big one as far as the footprint goes. This is the farm greenhouse gas budget. So this is the carbon footprint from the average. This is actually from grain farms, but similar thing applies. So we're looking about 30% coming from crop residues, and about 31% coming from urea fertiliser in itself. So fertiliser is the other big one, both in the production of it, but also when you apply it to the soil, you then produce nitrous oxide. When you start looking at electricity, other farm chemicals, fuel, they're actually very small parts of your carbon budget. The big one's that nitrous oxide. So what can we do about nitrous oxide? Well, we can basically optimise our fertiliser rates, because the losses that we see that you guys get hammered over all the time, going to the reef and all that sort of stuff, are the same processes that also drive nitrous oxide. And basically, I'm not going to go into this too much detail, but basically nitrogen fertiliser goes on as urea. The key loss processes, leaching, runoff, and there's one called denitrification. Now, I'm sure you've heard lots about leaching and runoff and how those DIN losses and DON losses and all that sort of stuff influence things. But do you hear much about denitrification? I don't know. But it's actually where our nitrous oxide comes from, so it's a big driver of our carbon footprint. But there's also this other one here called N2, or dinitrogen. So if we look at nitrous oxide from our nitrogen budget, basically if we put on 100 kilograms of nitrogen as urea, roughly about 1 to 2% goes off as nitrous oxide. So from an agronomic point of view, it's very, very small, but from an environmental point of view, it's quite important. Now, if we put on 100 kilograms of nitrogen as urea, about 40 kilograms goes off as N2. So much more important from an agronomic point of view. But N2 is 80% of our atmosphere. So it's basically what we're breathing in all the time. It's an inert gas. It's not very harmful. Well, it's completely harmless for the environment. But, you know, it hits your bottom, it hits your pocket, because, you know, it's basically fertiliser you're putting on, which is going straight up in the air. And this N2, because it is, you know, 80% of the atmosphere, it's also very hard to measure. So when we come and measure this stuff from a scientific point of view, we're using very, very expensive fertiliser. So, you know, complaining about your fertiliser bills, so our fertiliser costs $100 per gram, the fertiliser we use here, because we can trace it. It's very, very special fertiliser that we can trace through all these different processes. And it allows us to really get a handle on, well, where is our nitrogen going? Because the reality is, you know, these have been measured out in the reef somewhere, but this has not been measured anywhere. And if you're trying to close the budget when you've got 2 out of the 3, you know, maybe there's a bit of error there. It's a big unknown about what this one actually is. So we've done some research just up the road here in Burdekin, where we use this really, really expensive fertiliser. We measure the nitrous oxide, and we can try and actually break down, well, where is our nitrogen actually going? And what we found is, of the urea we put down, so if we put on 100 kilograms of urea, of nitrogen as urea, only about 16 to 26% of that actually gets taken up by the plant in any one season. Another 15 to 30% remains in the soil, so that might be utilised next season, might not. But over 50% of our nitrogen is actually lost. So where's that going? Well, you know, some of it might be going out to the Great Barrier Reef. You know, that's not great. But obviously this loss is a major economic loss for you guys as well. And importantly, as you can see, you know, that's not a linear line, that's actually curving up. So the more we put on, the more our system loses nitrogen. So it's actually not linear, it's actually exponential. So when we get up these really high rates, we're actually losing even more nitrogen than we are at the lower rates. But if we break down to where those losses are going, not all of it's actually going out to the Great Barrier Reef. A fair chunk of it is actually going up is that inert gas, N2, which has sort of been a bit missed in some of this conversation. So we can see this is from the 2 studies. This is Mackay, and I've covered it, but it's actually from Townsville, or the Burdekin. Yeah, a little bit of difference between the 2 sites, but actually Mackay, most of our losses are from that denitrification. So most of them are actually going up is that pretty harmless N2, that inert greenhouse gas. But of course it's a loss to your pocket because it's going up the atmosphere, not in the plant. Now the important thing is there, once we go above our 6 easy steps rates, actually our losses from denitrification are pretty consistent. So even at the low rates, we're still losing that much. I mean, that's just microbes are much better than plants at grabbing nitrogen. But once we get above our 6 easy steps rates, our losses really take off, and they're particularly bad losses for the reef. So another, I suppose, issue we need to deal with when it comes to nitrogen. And also our losses of nitrous oxide increase as well. So from a climate point of view, it's also not good because we're also increasing our nitrous oxide losses. Enhanced efficiency fertilisers, there was a slide on this morning, so I won't cover it too much. I think this was put up as well this morning. So basically, you can get a very similar return if you use them at 20% of the reduced rate. But what I'll show, which is a bit different, is that ignore most of this. What we're talking about here is an emission factor. So once again, this is the percent of nitrogen that we're putting on, which is lost as that nitrous oxide. Now, I said it's about 1 to 2%. The formal government emission factor, which is counted in the inventory, is actually 1.77% for sugarcane. Now, if we use one of those enhanced efficiency fertiliser products, we can actually reduce that to 1.2. So we get about a 40% saving. So the EEFs, you know, there's a lot of talk about using them for reducing stuff out to the reef, nitrogen loss out to the reef. Potentially you can do it cost neutral, but they also have a pretty significant climate impact as well. So it's another sort of positive story there. I'll just finally finish with this other technology, which is sort of just coming on board now. It's a bit underutilised in Australia. It's only just kicking off, but it's much wider in other countries. But it's enhanced rock weathering. So it's basically an application of crusher dust from basalt. It's a waste product from quarries and stuff for road base. But it actually, during its decomposition, when it breaks down in the soil, it actually sequesters carbon out of the atmosphere and locks it up as inorganic carbon. So it's actually permanently removed in the soil. And it can permanently remove 9 tonnes of CO2 for every tonne emitted in the process of crushing it, extraction and spreading it. So it can actually be quite a carbon positive technology. At the same time, it is also applying nutrients. So it's a big source of calcium, minor source of phosphorus, calcium and magnesium. Could potentially have a liming effect on soils, so it can reduce the acidity, which also helps then reduce your nitrous oxide and potentially also increases carbon. So this is a great win-win. Why have we not heard about this before? Well, because it's really, really expensive to do. You're looking at close to $300 to $400 a tonne, and the nutrients that are released from it, yes, they're valuable nutrients, but they're going to be released much, much slower than lime or your synthetic fertilisers. But because it's actually sequestering carbon, there's a potential that we could then use that carbon income to offset the price of it, and then these other benefits basically come as a free add-on. And that's the really exciting thing, is that we can do this as cost neutral. You can build your soil. If you know the beautiful black soils that we have up, I'm from southern Queensland, so the Darling Downs, that's our beautiful black basalt-derived soils, and we can basically, that's what these stuff is derived from. So really exciting. We're just trying to work it out and get the details of it, and particularly trying to figure out some of those agronomic advantages. But as a potential carbon sequestration pathway, it could potentially be a very cost-neutral one for the industry, which then give all these co-benefits around soil health, reducing synthetic fertiliser costs and whatnot. We've got a couple of trials happening here in Queensland. So this is down near Childers. So we put rock dust on twice now on a macadamia farm at 20 and 40 tonnes a hectare, and also on a sugarcane farm, working with a company called Carbonaut and also James Cook University to try and examine this new technology a bit more depth. Take-home messages: soil carbon is possible over very long periods, but it is challenging. But there's great opportunities there. We just got to be realistic, and don't believe the sales pitch. It's very context dependent, depends on your site history, soil type, management. There's some great new technologies. EEFs are pretty well proven. They can be cost neutral and still have a pretty big climate impact. I suppose there's still that, what's the incentive for farmers to do it? And maybe this is where the people buying your sugar should be thinking about that a bit more. But there's other ones, such as enhanced rock weathering on the horizon. Plan to inset first, and if you've got excess, then you can think about offsets. but you're never going to make huge amounts of money from soil carbon. There's a lot of risk there as well. Thank you.
Thanks, mate. Might take a few questions. Only time for probably a couple of questions, if that's all right. Here we go.
Thanks, David. Thanks for the presentation. I've actually got two questions. First one is, if we add high carbon sources like mill mud, mill ash, and say compost and biochar, would there be an opportunity for us to actually claim those credits because they're actually an introduction to our farm, which we wouldn't otherwise have there?
I did actually have a slide on this, but I took it out. So there's two very different types of carbon that you mentioned there. So the first was mill mud, and the second one was biochar. So biochar is very different. It's chemically inert. So it'll basically add it to your soil. It'll stay there for thousands of years. Mill mud and
Mill ash.
They're not. They'll recycle back, and they'll turn over within 1 or 2 years. So the microbes will break them down, and that's how you get the nutrients released from them, right? That's how you get your phosphorus, that's how you get your nitrogen, because they're breaking down the carbon to access those nutrients. So that's part of your normal nutrition cycle. Sugarcane soils, you're looking at 1.4, 2% carbon. A lot of that's because you're putting in lots of carbon. You're putting in far, far more carbon than we are out in the rangelands. But some of our rangeland soils are 3 or 4% carbon. So it's not the inputs, it's the fact that they're cycling so fast because of the climatic conditions and the soil types. So if you want a heavy clay soil, you're going to have a much higher carbon, and that's because it's better on holding onto it. So that's where if we look at our flux towers, the input's only half the story. The most important part of the story is, well, what's actually going on inside the soil, what bugs are breaking that down, and what bugs are releasing that carbon back out to the atmosphere.
Yep. So the next question is, do you actually think at some stage our governments, especially for us as cane farmers, we actually have high uses of nitrogen? Would we be better to actually be what was the word that you used, have offsets or insets? I suspect having an inset would actually allow us to continue to operate, whereas the offsets is probably what the mill's going to want long term because they're emitters. We're actually harvesting carbon. So where do you think we're going to go there?
Yeah, it's a tricky one because, as a beef farmer myself, I could potentially make income from offsets, but then if there is a regulatory change or the markets change, and I need to basically inset my own emissions, then it becomes problematic for me. But basically what that means is that the supermarkets are passing that cost on to me because I have to wear that cost as an opportunity cost around potentially selling that stuff. And that's a big issue. And it's going to be the same for the mills. It's going to be the same for the Coca-Cola, whoever. They'll pass those costs back onto the farmer. But in reality, that's probably the most likely scenario, even though it's probably not very, very fair, that it will be basically for you to sell your sugar into the future, you'll have to basically inset your own emissions. Now, it might be, I think it's going to start just in the high value markets, so it'll be a premium. A lot of banks and whatnot are looking at using it for low interest rates. Supply chains, so Coles and Woolies might give you a grant to go and implement something to, change your spreader so you can now apply this different type of fertilizer or something. So there might be some of those incentives, but in the long run, the reality is, the customer is not going to take up that slack. It's going to be paid for by the farmer, and that's where I think insetting is going to be the way it's going to happen.
Hey, David, how much research has gone into and what are the results of losses, as you say, from organic N versus artificial?
Yeah, so urea is basically your sugar hit, and so you'll get a big whack. But as you can see from those slides I said before, if we basically break down where that urea goes, only a very small amount of that actually goes from the plants. And that's because it's all there, it's all available all at once, and the plants are competing against all the microbes in the soil as well. Some of those microbes will be grabbing that nitrogen to bind up with the carbon, and that's what forms your soil carbon, which is really important. but also some of those microbes will also be using it to basically denitrify, and that's what goes, up as gas. Now, an organic source of nitrogen, it's just a slower release. There's evidence that suggests that plants prefer to take up organic nitrogen so that you might have a bit more recovery, but the same thing comes back to if you have more nitrogen, whether it's inorganic or organic, in your soil than the plants can physically uptake, you're going to have losses because you got your plants competing with your microbes, and if the plants aren't taken up, the microbes will do something with it and it'll be gone. So if you look at the same rates, yeah, potentially organic nitrogen is more efficient, and so you have less losses, but you can still have pretty big losses from organic systems.
Fantastic. Ladies and gentlemen, would you please thank David for all of his knowledge today and sharing. Thanks very much, mate. Good on you. Cheers. Ladies and gentlemen, we've got time for one more group of presenters before we break for afternoon tea. We've got a couple of presenters. Come on up, fellas. Ladies and gentlemen, Alex Olsen is Managing Director and Co-Founder of Auto Weed Proprietary Limited. And while Mustafa here is also an Associate Professor at JCU. Now, both are here to share with you their knowledge and research regarding smart spot spraying in sugarcane. This is a fascinating area. Ladies and gentlemen, would you please welcome Alex and Mustafa?
Good afternoon, everyone. Really excited to be here today and telling you about our project that is reducing herbicide usage in sugarcane farms across the reef catchment, using precise robotic weed control. We presented this project first when we were just funded in 2021 in Townsville for this forum. And at the time, we just were planning this project and we were going to do trials. Today, I'm really excited to share with you, with Alex, the result of our work. We have done a number of trials. We'll tell you a bit more about them, but we have seen tremendous result. So let's get on to it. What is our technology? So to put it simply, we put the herbicide where it needs to be put, on the weeds. And that's the only place it needs to be put. How do we do it? Compared to blanket spraying, that you blanket spray the whole paddock, we use AI, artificial intelligence, to find out if there is a weed that I need to spray. And that's simple because that way you can reduce a lot of herbicide, especially if you have a low weed infestation. Today in the morning we heard about the sustainability requirement, that we are moving toward more sustainable solutions. So we also heard about maybe soil health that would be benefiting from a reduced herbicide. So this technology can actually be a winner and a good sort of balance for reducing the input cost for farmers, at the same time saving serving these other measures. So you may ask how it works. So the technology is based on deep learning. This is that AI part. This is the same thing that you would have on your mobile phone when you unlock your phone with your face. This is the AI that is basically has learned your face that first time that you were rotating your head. So that's where the AI learned the features in your basically face. And the same goes for weeds. They have different shapes and colors and edges. And you need to teach the AI this. And we use computer vision. Computer vision is what? It's a fancy word for some good cameras with some good resolution. And here we are using RGB cameras, normal cameras that you would have in your mobile phone. It's not like VDID and VidSeeker that we're using near infrared. And because we are using these features, we can actually detect weeds based on their shape, even if they are in their surrounding environment and in a green-on-green basically setting. And that's the good thing about this technology. The only thing is there is a catch. You need to show many instances of weeds, thousands of instances of these weeds, so that the algorithm learns. And that's actually bring me to my next slide. So if you tell me that I've got this paddock with, say, I don't know, plant cane and some nutgrass or some broadleaf, and you say, I want to just apply Sempra or Crismet or other things, you say, okay, let me just go and collect some images, 20,000 images, and 20,000 is not many, so we can just cover one row and 5-10 minutes, and we already collected 50,000. So we go back and then look at these images, manually label some of them, and say, okay, this is the weed in this image, and we match this to that image and feed it to the algorithm and train the AI to learn what the weed is like. And then after that, this training is just like the tricky part. So after that, we go back and deploy it in our detection units in the field. And so this was developed in a PhD project that Alex did at the time, and I was the supervisor at James Cook University. Alex then went on to just start his own company, AutoVeed, and then in 2020 we saw this call from the Reef Trust Partnership, and Alex and I were talking and said, okay, this is a no-brainer. They are calling for innovative project that can reduce herbicide and improve water quality. So this is us. And then we started developing the application. We were very fortunate to be funded in 2 rounds. So far, we have received 2 rounds of funding to basically develop our prototypes and do sugarcane trials in the Burdekin region, and to compare our technology, the spotter spraying, to blanket spraying. Alex will tell you a bit about the prototype that we have developed, but what we wanted to achieve and measure was just, what is the weed knockdown? How effective is our technology compared to blanket spraying? Because we want to be very close, right? At the same time, we wanted to see what is the herbicide usage, comparing these 2 technologies, how much we can save, and the water quality benefits that we may get. In the second phase of our project, we are also looking at the economic implications of the technology to see how much would be the saving that is possible through this technology. Alex will tell you about the development of our prototype, and then I'll come back with some results.
Thanks, Mostafa. Yeah, so I can share what we've done with AutoVeed, developing the prototype, engineering prototypes. Now, it's worth mentioning we aren't just taking something off the shelf and trialing it. We actually built the solenoid circuit boards that drive our solenoids. We developed the software. We integrated the camera system. We made the housing ourselves, all out of Townsville. So we're based on Ingham Road in Townsville. And then we put it on the tractor, retrofitted the system, and tested it in the field. So there's a fair bit that's gone into this because we're our own startup developing this technology. The prototypes we developed in close consultation with Sugar Research Australia, particularly Terry Granshaw in the Burdekin region, and Emily Fallols up north, and Dylan Weedle down here in south, basically to figure out what are the systems that we need to build to test in sugarcane. And that was a high-rise sprayer was our first system. That's a 13-row high-rise. That was Phil Corica's, a spray contractor in the Burdekin region who we fitted to. And a 4-row boom sprayer. This is SRA's 3-point linkage system, just a 4-row, so a bit more maneuverability. And we also have fitted an all-terrain vehicle, just a quad, and a UTV for data collection. Those smaller vehicles allow us to zip into a site, collect a bit of data, and we're ready to spray like within 2 to 3 days after getting that data collected. But the prototypes that we developed, this is the 13-row system up here, and this is the 4-row system. You can see those little hats. That's our units with a little sunshade. Each unit, AutoVeed detection unit, sees about 1.6 meters across. So each one can see 1 sugarcane row each. So you'd have 1 unit per row. We also fitted the system to be suitable for urban leg spraying, which is a key requirement in the Burdekin region and north and south as well, and broadcast spraying. So both of these systems here, we could fit for urban leg or broadcast spraying. One thing I'll note, we also calibrated the system to be run at 8 kilometers per hour. So to run our artificial intelligence algorithms, we need to process them really fast. We need to make a decision in like 20 milliseconds. And the distance between the nozzle and the camera is also set for this 8-kilometer distance, 8 kilometers per hour. However, that can be changed. If you have a more powerful processor, you can get higher speeds. And if you increase the distance between the nozzle and the camera, you can also get higher speeds. So we've had a few different systems, and it's been a really great learning curve building these systems fit for purpose for cane. One thing we were really happy with, just about, I think a month ago, we finished the installation of a dual tank sprayer. So SRA had a 2-tank solution with 2 lines, and we can actually make 2 decisions at once. Spray grasses and broadleaves in a single pass, making 2 detections. And we're ready to trial that for our next spray trial, so that's really cool. Just pressing next. There we go. So here's the systems in action. The one on the left is the 13-row high-rise. That's on a ratoon cane paddock spraying nutgrass. The one on the right is a rotational mung beans crop. That was in Mount Kelly, Scott Matthews paddock. And the first one was Steve Pillar's block near Horseshoe Lagoon. You'd see it just on your way to Townsville. Here's our dual tank sprayer. We had a field day just about 3 weeks ago or so, where we tested this unit with a really good, it was great. We had a bunch of growers out in the Burdekin region to watch it actually spraying. So it's spraying blue herbicide on the grass, and it's spraying red herbicide on the broadleaves. That was our first trial of that system, just in a demo capacity, just spraying water. But it was really cool to get the growers in there, having a look at it and watching it spray. Before this one, we also did a field day in Home Hill as well, and that was just a tremendous one too. We targeted nutgrass and had everyone in having a look at it. This is quite new for us too. This is an LED system that we've put at the back of the camera. We had some issues with shadows that we're going to talk about in a minute, and we put some LEDs on to bring the lighting up to have a consistent image. It turns out that it allows us to do nighttime spraying. And just last week on Paul Villas's property in Ayr, we had our first nighttime application where we didn't mean to spray at night, but we ended up not getting started until about 5:30, and we ended up going all the way to 8 o'clock. And whether we wanted to or not, we were testing nighttime spraying. Fortunately, the LEDs proved fantastic, and the image, the detection looked just as strong as daytime spraying. We're currently analyzing the results to see if our efficacy during nighttime spraying is as good as the daytime. But it's really cool to see this. Paul came out because we were at his place. The paddock's just beside his house, and we're there till 8 p.m. And he's like, "What the hell is that in my paddock? It looks like it's burning the cane or something, burning the soybeans," because he sees this bright light, but it's just LEDs. There's no danger, but it looked really cool. The trial design. So we established a trial design really to nail down on that simple question: are we saving herbicide compared to spraying the whole crop? And how many weeds are we killing versus spot spraying versus blanket spraying? Is it effective? To do that, we divided each trial paddock into like 12 or 13 row sections. We spot sprayed the first, blanket sprayed the second, and so on and so forth. Then we measured weed knockdown using drone technology, and I can shed some more light on that. Herbicide measurement was easy. We just read off the flow rate controller or the tank. And water quality improvement, that was a bit more in depth. We had to come back after irrigation-induced runoff and take some grab samples and send it back to the lab at SRA to compare the difference between the treatments. Weed knockdown, yeah, drones are fantastic for this type of stuff. Like if you're doing a crop intervention and you want to see if you can find a reasonable impact has been made, drone technology is the answer. In our case, we flew it at about 10 meters height, really low to the ground. That had 2 millimeters per pixel resolution, meaning we could really have a good look at these weeds. And we came back after the spray, like depending on the chemical, 5 days to see the effect. And we could line up the images with georeferencing and then just count. How many weeds did we hit? How many weeds did we miss? What was the kill rate between blanket spraying and spot spraying? This is the map here. I think this is at... it might be Old Clare Road. This was spray trial 6 on a nutgrass paddock with Alan Richardson, his block. And our drone maps were just random samples at parts of the paddock. Those coloured squares indicate the different treatment zones that we're looking at and counting weeds. This is just a quick visual snapshot before and after. This is a blanket spray. This is a nutgrass infested block at Steve Pillar's place. We sprayed it with Crismat. So it had a burning off of the nutgrass. You can see it turning yellow. That was our visual cue to count a hit. This case, the blanket spray was pretty much 99% effective, I believe. And the auto-weed spot spray for this one was fantastic. We had a really good kill rate. Just wait for the animation to load. I did this in the last presentation too. Let me just... Oh. There we go. But in this visual example, the spot spray was just as effective visually as the blanket spray, and that was backed up with our counting data that Mostafa is going to go through in a second. One other very valuable output from this work are spray maps. This is a new piece of data that hasn't existed before. You do have application maps when you spray a whole block with your John Deere rig or your Ag Leader rig, but this is a spot spray map of where I sprayed my chemical. It's also a weed location map, which hasn't existed before. So just think about how valuable that could be. Like if in an audit you know exactly how much chemical you've put down, that's really good information to have. But also the historical weed locations could be useful just to track your performance for any of your weed control methods over time. But one other very interesting research question might be, if you were to selectively apply pre-emergent only where the weed seed bank is, would you get effective pre-emergent holding of that paddock and with less pre-emergent usage, saving money? We need to answer that question. We haven't done that as part of this work, but it's possible, depending on the weed. Like if it spreads anywhere, then it might not be a candidate for that, but it's interesting to note. I'll hand back to Mostafa. This is the results from all of our 9 trials. We have just finished 2 more trials in the last 2 weeks at Paul Villas's property. So we've done 11, but this is the first 11. So I'll hand over to Mostafa.
Yeah, so with the methodology that Alex explained, we went back to just like look at all these trials. These 9 trials, if I add them up, they are about 47 hectares done across 3 years. But Alex and the team, we have done recently another, I think 23 or maybe in 20, maybe 40 hectares in 23, 24 so far. Yeah, almost. Yeah, so these are different, basically, trials. The blanket spraying is the blue bar, and the green is the spot spraying. And you expect that the spot spraying is always better, right? So the thing is, if you have a higher weed infestation, you'll get a better green bar, and that means lower. So, and if I want to show that, this is how the actual line is showing the weed density. So, and we see a clear basically agreement between the weed density and the amount of chemical that you put for a spot spray. And same for trial 6. For example, trial 6 was a plant cane with nutgrass, and 1/3 almost was the amount of herbicide that we applied because it was patchy nutgrass. But we have here like another interesting trial, trial number 7. I think that was paraquat, Alex, and a few others. I think D4D.
Yeah, there was a paraquat mixture there. There was a pretty dense paddock, and we had an issue due to shadows. So you can see that green bar, the green bar should be up near that yellow line. So this was our worst result in terms of the trials, but it was a really good learning lesson because we discovered something with the technology that we really needed to solve. So happy to shed light on that.
So that was another interesting, and as Alex said, we saw this problem. And then we went back to think about it and see like 2 different ways that we come up so far with. So now this is weed knockdown. You may ask, okay, what was the weed knockdown? How effective is this compared to blanket? So if you look at all these bars, they're pretty close, except for trial 7. We have missed many weeds. Some others, they basically are pretty good. But across these whole 9 trials, and we don't have trial 1 because we had a bit of issues with a drone. But if I want to, those were too many bars.
It's worth just mentioning too. Yeah. Shadows was the thing. We don't want to leave you waiting on that. What went wrong with trial 7? It was shadows. That the shadows in the day we went to actually do the spray job, it was very overcast. And when we did our data collection, it wasn't overcast. It was fully sunny. So our data set didn't match our trial situation, and the shadows that were present resulted in missed weeds. That led us to adding those LEDs to the system to solve the problem. And since trial 7, we've been using LEDs to solve that solution. Sorry, Mostafa.
No, that's okay. I mean, yeah, it was also like that trial showed us that shadow can be a problem. And again, I'm a researcher, I'm a scientist. I like to just solve this problem, not with the easiest way that comes to mind, maybe LED. I was thinking, can I do AI to remove the shadow before feeding this image or video to another AI? And it turns out we can, and we have actually done a lot of interesting research. At least to me, it's interesting. So that we are currently working on, and we will add that. But whether we go with LED or not, that's another question. So too many bars in the previous slide. Let me just summarize them. On average, weed knockdown with our spotter spraying technology was 95% as effective as blanket spraying, and that's while reducing herbicide by 35%. And that's the big sort of win for 35% reduction in herbicide, and in best cases, we had about 65 to 70% decrease in herbicide usage. And if you want to look at the liter per hectare numbers, those are down here, so across these 47. And so that means that if you have less weeds, this is the technology for you, and you will have more saving. So, and then water quality, with Emily Fellows, she's actually leading the water quality trials, and we collected end-of-row samples, and 3 to 6 days depending on the chemical, and we analyzed the data in SRA labs to see what is the benefit that can come from this technology, how much reduction we can see in the chemical, in the actives that are running off from the farm. So on average, we saw that spot spraying reduced the mean concentration and load of herbicide in the runoff by 46 and 61% respectively. So that shows that it can actually reduce these chemicals that are running off to the reef significantly, and shows the potential of the technology, that sustainability that we had today, and that even soil health that we had today. So those sort of things can actually be achieved at the same time as maybe some saving that you can have with the technology. So just one final slide. Alex will tell you a bit about these extension activities that we have done, because we have been fortunate to get a second round of funding to be able to just do more than our initial work. Alex?
Yeah, just quickly, yeah, we're very thankful to the Great Barrier Reef Foundation, and Carolyn's here today, our program manager, to extend our work. Our original 6 trials did 30 hectares of spraying. In the second extension phase, we've now done 41 hectares as of the 2 we did last week. We've done a lot of technology development by improving shadow performance with those LEDs, and unlocking nighttime spraying has been tremendous. Beefing up our user interface, so now we just use an iPad to control the system when it's in the field. That makes Terry Granshaw a lot happier. He drives the tractor for all of our spray jobs, and he's just been a big help. So he's not here today, but big thanks to Terry for all of his support. And we've also expanded data collection. All these trials are in the Burdekin, but we've also started collecting, with the help of Dylan Weedle from SRA, data sets in Mackay. Guinea grass in about 9 different paddocks across the Mackay with Sunday's region, to build models so that we're ready to start working for the Mackay region, and as well as up north in the wet tropics. So, and one more thing, the economic analysis. We've been partnering with DAF, with Mark Poggio in Townsville, to look at the return on investment for this type of technology, particularly looking at our case studies that we've done so far, and how it's going to be best benefiting the growers, and how that's going to work. So there should be a case study coming out soon that'll be really good to share with you. Thanks very much, everyone. Happy to answer any questions.
Thanks, fellas. Folks, we've only got a few minutes for any questions. Please.
Very quickly, not real clear about understanding, once you take the photos of the crop, can that information, obviously it's in the system somewhere, be relayed off to another field, or do you have to do a data set for each particular field? And the second question is, how far away do you see this reaching the ability of being able to do it at 15, 20k an hour?
Yeah, thanks. Awesome questions. The first one, no, you don't need to collect data for every single paddock. You just need to collect data for individual paddock scenarios. So, for example, if you have a nutgrass in early plant cane situation, and which we do, we've collected data in that situation, in the Burdekin, it's very likely that our data will hold for similar paddocks. And we've tested that because our trial 3, we didn't collect any data from the trial 3 paddock. We just collected data from trials 1 and 2 paddock. And those 1 and 2 models held for number 3. It will change, however, like a small difference in background soil type. So if you have a grey soil and a dark soil, it's likely that data collected in a grey soil won't match the dark soil. So we have to build our data set with these different scenarios in mind. Yeah.
I want to add something about this. Was a really good question. This is a deep learning AI question. Usually, what Alex said exactly right. 1 and 2 and 3, by the way, are on the same property, like different blocks, right? So they're pretty close. But the algorithms learn the general features. They say, yeah, this is the cane, maybe this is the thing that you want to capture with your data is the corners. Corners meaning, no, I don't want the same, thousands of the same image. I want 10 of a different sort of image, maybe in a different light, or maybe when there is a bit of, I don't know, rain, because that captures the corners, the differences that you would, as a human, very quickly pick up and say, this is the same thing, right? But this is the key point here. You cannot have a one model fit all, definitely, but you can, if you are adding these newer images that you collect to your data set, go back and retrain the model and refit it again and again to make it better.
Yep. Oh, there was a second part to that question too. That's all right. The speed. Yep. Time is definitely the answer, but also for the speed, the engineering prototypes we built here, we built them in 2019 using the computing technology we had from NVIDIA. It's already gone leaps and bounds ahead, and at the same price point that we purchased these units at, you can get 8 times as fast processors. So the industry is moving really fast, and we could actually build, what, just 15K an hour, 20K an hour? I would have no problem saying that we could do that today, like, at all, yeah. Yep.
Alec, just quick, I think you answered it, but can you put your recognition camera before your spray camera and self-learning at the same time, instead of having to do pass first?
What's that? So
you're learning. You got to send out your ATV first.
Oh,
so
yes.
why can't you do that at the same time?
So collect the images. Oh, so every time we spray,
Yeah,
we're
while you're
still
spraying.
collecting. Yeah, no, yeah. That's 100% right, Dennis. Like, it would be a missed opportunity if we didn't collect all of the data when we run these units. And so we do that. We every time we do a spray job, it's collecting more data, and that's the value of getting these cameras. Yes. And like, so the ATV is in front of the tractor and it's got to like send its information to the tractor behind it. The only thing there is to move that data off the ATV to the cloud or something and then send it back to this tractor in real time is pretty tough. Yeah. Is that to just increase the spray distance? No. Oh, get more information. Yeah. Yeah.
Online learning. So you're talking about zero-shot learning here is just like, I haven't seen something, but I've seen many similar things, and I can just say, yeah, I haven't seen this room, but I have seen many chairs, and I haven't seen this chair. I can detect that. In agriculture, maybe it's a bit more challenging, but that's a really interesting. So zero-shot learning or few-shot learning are things that are happening, and we haven't implemented here because it's just we have limited resources. But definitely, these are all really interesting questions that definitely we can look at. Sorry, we went.
No, quarter on. Ladies and gentlemen, unfortunately, we've run out of time. But please pick these guys' brains. Would you please thank Alex and Mostafa, everybody? Good on you, fellas. Ladies and gentlemen,